because there's not much on Le Chatelier's principle on A2, I've switched to AS, and I've switched to AS paper 2019, because here's a big one and it explains everything to do with Le Chatelier's principle. So I've got a reaction. I've got carbon monoxide and 2 moles of hydrogen making methanol. So I'll do reveals on this. The reaction uses a copper-based catalyst at a pressure of 10 megapascal and a temperature of 550 Kelvin. These conditions are used to provide a balance between equilibrium yield, reaction rate and cost. Describe how the use of catalysts and change in pressure and temperature affect the equilibrium yield, reaction rate and cost. So it's pretty much everything this. So I've got some carbon monoxide, 1 mole of carbon monoxide, 2 moles of hydrogen, making 1 mole of methanol. So I've got 3 moles on the left and 1 mole on the right. It's the delta H, the enthalpy change, as the heat change at constant pressure. It is minus 91 kilojoules per mole. So it's an exothermic reaction. So let's have a look then. So enthalpy change is negative, it's an exothermic reaction, it gives out heat in the forward direction, that's when it goes left to right. Therefore, to increase the yield of the methanol, if that's what we're trying to do, if you lower the temperature by Le Chatelier's principle, it will oppose that change and try and raise the temperature. It would raise the temperature by shifting the position of equilibrium to the right because it's exothermic and going to give out heat to the surroundings in that direction. So if you lower the temperature of the surroundings, it will increase the temperature of the surroundings by shifting the position of equilibrium left to right and making more methanol. The problem with that is that if you lower the temperature, then the reaction rates in both forward and backward direction drops. So yes, the forward direction will increase in reaction rate compared to the backward rate, and it will shift to the right hand side, but both forward and backward reactions are lowered in terms of their rate. They both start to go really slowly because fewer particles will have the activation energy, the minimum energy to react, and so therefore it'll take a long time to reach that equilibrium. So that's why a compromise temperature is used, 550 Kelvin. It means that more particles have the activation energy, the energy needed to react, so the equilibrium will be reached quicker, but you do not get as big a shift to the right hand side in terms of position of equilibrium, because you've used a slightly higher temperature. It's also going to increase cost as well, but you have to compromise. We said there's 3 moles of gas on the left and 1 mole on the right. The gas on the left hand side of the equation take up a larger volume. So if you use a higher pressure, by Le Chatelier's principle, it will try and lower the pressure. It will lower the pressure by lowering the volume, and it will shift the position of equilibrium to the right hand side. A higher pressure will give a faster rate as well. It won't increase the activation energy, so it's not as good a factor in increasing the rate as temperature, but it will bring particles closer together, so you'll have more chance of successful collisions between those particles which do have the activation energy. So that's why it's used a high pressure, 10 megapascal, which is 10,000 kilopascal. 10 million pascal. It's a big pressure on megapascal, so again, increasing pressure is going to be costly. Would a catalyst do anything? Yes. Well, it will provide an alternative reaction route, and it will lower the activation energy and speed up both forward and backward reactions. It won't change the position of equilibrium because it increases the rate of forward and backward reactions equally, but it will mean that the equilibrium position will be reached more quickly. So remember, equilibrium is when the rate of the forward and backward reactions become the same and no longer change, and the concentrations of the reactants and products no longer change. So the equilibrium position will be reached more quickly, and so that's going to save on cost.